All right. So obviously we talked about two different types of bonding, really three different types of bonding. We talked about ionic bonding, which, as we talked about, it's always between a metal and a non-metal. That's always going to give you ions. And again, there's no sharing of electrons. So we get that because, as you saw today in today's experiment, metals and non-metals have very differing sort of periodic trends. And when those two get together, we always get basically the metal giving up its electrons, the non-metal gaining electrons. And again, that's what's creating our ions that hold that together. We also have covalent bonding, which is between two nonmetals. And again, that's because our location of the nonmetals are in the same location on the periodic table. They're just going to share. And as we talked about earlier, the sharing can be basically one of two things. It can be what is referred to as a nonpolar covalent bond or just simply a nonpolar bond. And that is where you have what they consider equal sharing of electrons. And basically, the result of that equal sharing of electrons is that you will create a bond that's basically like a neutral bond. So the distribution of the electrons over the two elements within that bond is going to be pretty equal and not create a side that's more positive or more negative. And that is different than the other type of covalent bond, which is known as a polar covalent bond. And that is going to create differences in electronegativity, which is going to create differences in how the electrons are shared. And they will no longer be shared equally. And one of those guys, like we talked about earlier, kind of like a tug of war and pulling on the rope, one of those guys are going to pull on the rope and bring those electrons closer to themselves. The result of that is we no longer will have kind of like a neutral bond. We will have a bond where one side becomes more partially negative, the side that has more electrons near it, and one side that will become more partially positive, where the electrons are moving away from it. And that, again, is what's known as a polar bond. We could represent that with that arrow that we drew earlier. And again, that arrow, which is sometimes referred to as a dipole arrow, always points to the side that is more electronegative and more negative. And the back part that makes like the little plus sign is the part that is in the more positive direction as we go there. As we finished up on here talking, this is again the table of electronegativity values. You do need to know the general trend in electronegativity. These numbers would be provided for you if you needed them. But we could take the difference in electronegativity values between the two elements involved in the bond, and that will help us determine whether or not we should expect sort of a polar bond, a nonpolar bond, or really even an ionic bond. But as we talked about earlier, you really don't need it for ionic because you just need metal, non-metal, it's ionic. So once again, if the difference in electronegativity is between 0 to 0.4, that is considered equal sharing of electrons and will create, once again, a nonpolar bond. If it's above zero point 0.4, which is like zero point 0.5 to less than 2, that's going to create some unequal sharing of electrons. And once again, that's going to create a polar bond in this case. And typically, if you're over 2, that's going to create a ionic bond. So I did a few that we did earlier to take a look at it. So why don't you try calculating a few of these here? Let's say we have the bond between carbon and oxygen. Let's do sulfur and oxygen. Let's do carbon and hydrogen. Let us do carbon and sulfur. And let's do the bond between potassium and chlorine. So use the difference in electronegativity values from this table to help you decide, is this bond going to be ionic, polar, or nonpolar? So take a few moments there and again decide that kind of polar, nonpolar, or ionic. Okay, let's take a look and see it. As I talked about before, you basically just take the bigger number minus the smaller number. So we come up here to carbon, we see it is 2.5. Oxygen there is 3.5. So if we calculate the difference in electronegativity, which is what that delta En stands for, we're just going to take 3.5 minus 2.5. That is definitely going to give us a difference of 1. That is above 0.4, but less than 2. So this tells us this bond should be polar. And if I were to draw the arrow here, it should point towards which element? It should point towards the more electronegative element, which is the oxygen. The oxygen in this case would be more partially negative. And the carbon in this case would be more partially positive as the oxygen is pulling the electrons closer to itself versus the carbon in that case. Question on that one there. Next one, we got sulfur, which is 2.5, and oxygen also 3.5. So this is going to give us the same deal. We're going to end up with 3.5 minus 2.5, going to give us 1. That again tells us it's going to be polar. And once again here, we would draw that arrow pointing to the oxygen. Oxygen should end up being more negative than the sulfur in this case, as it's more electronegative, bringing the electrons towards itself. We take a look at KCl. We really don't even need the electronegativity values. That's a metal and that's a non-metal chlorine, right? So automatically, I know this is ionic, but if we did calculate in this case, potassium is 0.8 and chlorine there is 3. That's going to give us a difference in electronegativity of 3 minus 0.8, so 2.1. That definitely is above 2. But once again, you really don't need these values to determine that. As soon as you see metal, non-metal, it's ionic all day. Don't even waste your time with electronegativity values. You know, you can figure it out just basically based on that. Carbon and hydrogen. So carbon being 2.5, hydrogen being 2.1. Difference in electronegativity here going to be 2.5 minus 2.1. That is a 0.4. That is the cutoff for nonpolar. And that means that this bond is nonpolar here. Now, the reason for this is, as we just saw in the experiment we did, heptane is made up of all carbons and hydrogens, and it is a nonpolar compound. Most organic compounds are made up of carbon and hydrogen, and they are non-polar, as we saw in the experiment. And that's really why the upper limit cutoff there is 0.4, is to handle the carbon-hydrogen bond, which is a non-polar bond. Now, is the carbon and hydrogen perfectly equally sharing electrons in this case? They are not. There's a slight 0.4 difference. So it's not perfect equal sharing of electrons. So we would not classify this as a pure covalent bond because there is a slight difference, but not enough to be considered polar. So it's still considered non-polar, but is not a perfect equal sharing of electrons. Any questions on that one there? Carbon 2.5 on the next one there. And sulfur 2.5. Dare I say, when I do the difference for that one, that's going to be 0, I hope, right? 2.5 minus 2.5. It's going to be 0. That's going to make this bond non-polar. That bond, though, is actually pure covalent, right? It is perfect equal sharing of electron based on electronegativity values. So this brings up a really good point that you definitely can have two different elements that actually share the same electronegativity value and will create a nonpolar covalent bond. You definitely will have a nonpolar covalent bond when you have two of the same elements coming together. Why does that happen? It is what is sometimes referred to as the diagonal rule on the periodic table. If you look at the location of carbon and sulfur, they are diagonal of each other, not perfectly right underneath each other, but kind of down and over to the right. And because carbon is higher up, but sulfur is further to the right, they cancel out their differences and they end up with the same electronegativity value. That happens in a few places. If you look at nitrogen and chlorine there, also the same electronegativity value. So there is possibility of this sort of diagonal relationship that can develop between two different elements that may actually share the electrons equally. But again, it's usually over one to the right, not directly below it, kind of one and over to the right to cancel out those differences. Now, when you are looking to determine if a bond is polar or non-polar, do you really need the values in all cases? And the answer is, in a lot of cases, you don't really actually need the values to make a pretty educated guess on whether or not something will be polar or non-polar. For example, if we take a look at our carbon and oxygen, they are in the same row on the periodic table. And what we know in terms of the general trend in electronegativity is it increases as you go to the right on the periodic table. So since these two are in the same row and oxygen is further to the right, it should be more electronegative, and that should create a polar bond without even needing the numbers. So if you're comparing somebody in the same row on the periodic table, and it's definitely non-metal sort of action there. If somebody's further to the right in the same row, probably going to create you a polar bond. You probably don't have to worry about the numbers, and you know the one further to the right should be where the arrow should be pointing. Now, if we compare sulfur and oxygen, which was like this other one here, they're actually in the same group on the periodic table. And what we know in terms of electronegativity is it increases as you go up and to the right on the periodic table. So once again here, oxygen is further up in that group, which would tell us it's more electronegative than sulfur, and you don't even really need the numbers. Once again, that's going to probably be enough to create a polar bond for you, and you don't actually have to do the calculation. So there is a lot of situations where just by using the general trend in electronegativity, you can make a pretty good estimate or guess as to whether or not you would create a polar bond or not, especially if you're comparing the same row or same group on the periodic table. Any questions on electronegativity and how to use it there? Once again, what we are talking about here in most cases is what is referred to as bond polarity. All we are simply determining is between these two elements how the electrons are being shared. Are they going to be shared equally or unequally? It may not tell us how in an entire molecule the electrons are going to be shared equally or unequally. There's a few other things we have to look at in that situation. So once again, this is sometimes referred to as bond polarity. So as we saw there, when we get widely different electronegativity values, that definitely is going to lead more to an ionic bond. And that, again, is what happens when we take a metal on the left-hand side of the periodic table and hook it up with a non-metal on the right-hand side of the periodic table. When we just stick to the right-hand side of the periodic table on the upper side, we get all non-metals, similar electron negativity, and tend to lead to covalent bonds. And as we talked about before, those are the general things that make up those two types of bonds: metals, nonmetals, ionic, two nonmetals for covalent. All right. So this is sort of what we talked about. And uh, as I mentioned earlier, that kind of two cutoff for ionic is not perfect. There definitely is combinations of metals and nonmetals. They'll get you a electronegativity value less than 2, but that's why you can default on the metal and nonmetal. We don't use it all that much here in this class or in most classes that you talk about, but instead of sort of polar and covalent, polar and nonpolar, sometimes people used to talk about percent ionic character of a bond. And if you're 100% ionic character, that means you pretty much have an ionic bond. If you're 0%, you pretty much have a covalent bond or a pure covalent bond. Most people stick to polar and nonpolar, but some people will use sort of that percent ionic sometimes as well. All right. All right. The next thing we're going to talk about is actually the steps in writing or drawing Lewis structures. So earlier in this chapter, we talked about how to draw sort of structures for ionic bonding. And what we're going to talk about here is really structures that involve covalent bonding. Now, it's really important to sort of follow the steps in order, and it will usually lead you to the right sort of picture. If you decide not to follow these steps and do what some people do, which is, I call it kind of piecework, they try to take every individual element, every individual, how many valence electrons they have, and try to figure out how it all comes together. They usually will end up with a bad Lewis structure, too many bonds, not enough bonds, too many electrons, things just kind of go bad. So the first thing you want to really think about when you're drawing a Lewis structure for covalent bonding, which is sharing of electrons, you want to figure out how that thing is sort of put together. And there are a couple of rules to help you follow to determine sort of how to put things together. The first main rule is whatever element is the least electronegative atom is usually in the center. And in a lot of cases, everybody else is attached to that. There can be multiple center atoms, but usually a lot of things that we come across in this class will be like one guy in the center and then multiple things sort of attached to it. but you definitely can have multiple centers as well. One of the two things that should never ever end up in the center is fluorine, because it is the most electronegative element, so it never should be in the middle when you're drawing. And our friend hydrogen that we talked a lot about earlier should never be in the center, and that is because hydrogen should only have how many electrons? Hydrogen should only end up with 2 electrons, which means if you put it in the center, it's going to have way too many electrons attached to it. So as I mentioned before, hydrogen, once again, on the outside, looking like that, basically, is what hydrogen should basically look like. No dots, nothing else on it. The next thing you want to do, which is probably almost the most important thing, is you want to count up how many total valence electrons your picture is supposed to have. Now, that number is really important because when your picture is done, you got to have exactly that number of electrons in your picture to be correct. Now, there are things known as polyatomic ions, which are things that share electrons but actually have a charge. And if you have something with a charge, you do have to take that into account. And if something has a negative charge, that means it's gained electrons. So you do need to add an extra electron in. And if something is positively charged, you need to subtract that positive charge. Cut and paste there badly. So if it's a positive ion, you should have a minus the number of electrons there from your total. Otherwise, if you don't, you will end up with some unpaired electrons, or you'll end up maybe with too many electrons that you shouldn't have, and that's not good. So if it has a charge, you need to adjust it. Once you have the logical arrangement and you know how many electrons your picture should have, you want to make basically one bond from the center atom to each outside atom. These are single bonds. And this is your choice. You could use a line like we talked about earlier to make the bonds. I personally use lines, or you can use 2 dots to represent a single bond as well if you rather use dots along the way. Once you do that and you pretty much have your central atom and you connect it to everybody on the outside with one single bond, you're then going to have a certain number of electrons left over at that point. Those will then go on the outside atoms in pairs of electrons. So you start filling up all the outside atoms with electrons in pairs, and those will be dots. Those are some non-bonding electrons, some lone pairs. You're going to fill up all the outside atoms until each atom has the magic number of 8, except if it's hydrogen, right? Because hydrogen will not get any dots. It will be done at that point. If you fill up all the outside atoms and you still got electrons you need to put on your picture, then you go to the center and you put those on as pairs of dots as well. So you want to work on the outside in, basically, yeah? And we do single bond to everybody first, dots on the outside till everybody has 8, and then if you still have electron, dots on the central atom. At that point, you will pretty much be out of electrons once you get to the central atom. The last thing you want to do is make sure everybody has met the octet rule, except for hydrogen, which obviously should meet the duet rule, which is only 2 electrons. It's at that point, if somebody does not meet the octet rule, you want to try to fix it by making a double bond. And you want to use all your options for double bonds. And if the double bonds don't fix the problem, then you go to triple bond. So this is what I was talking about earlier. You do not want to just double bond and triple bond right out of the box. You want to go single bond first, then double the fix, and then if necessary, triple the fix it. And that usually will give you a pretty good picture when it's all said and done. Now, the thing like I was talking about before, you don't want to do some piecework, which is what people sometimes do. Like nitrogen's got like 7 and oxygen's got 6, and try to figure out how they come together. You want to think of the electrons here when you calculate the total number of electrons as not necessarily belonging to anybody, but you want to kind of evenly distribute those electrons as best as possible in your picture, and that will allow you to get the right picture rather than like, okay, I got to put an extra electron on nitrogen. He's got 7. That's his electrons. So you don't want to kind of think about that when you're drawing these type of pictures. You just want to think about the electrons as just trying to be distributed over everybody. Any questions on that there? All right, that's a lot of talk. So let's talk about how we would do something like this. So let's take an example like this, and I'm going to draw it higher because I know it's kind of hard to see in some spots of this room. So we're going to go NF3, and we want to draw the Lewis structure for this. By the way, we do know it's covalent bonding because nitrogen is a nonmetal, fluorine is a nonmetal, so that's going to be some type of covalent bonding and sharing of electrons happening here. So really, the first thing I would do in this case is add up the total number of valence electrons. Once again, the valence electrons equals the group number. So if you go to the periodic table, you will see nitrogen in group number 5, which means it's got 5 valence electrons. There are 3 fluorines. Each of the fluorines are in group number 7, which means it has 7 valence electrons. And that's a grand total of 26 valence electrons. And again, that number of 26 is really important because your pictures has got to be exactly that number when it's all said and done. So now we want to think about how this is arranged. So remember, in the center, we want the least electronegative atom. And as we just talked about, definitely up and to the right, fluorine is the most electronegative, so it should never be in the middle. So the logical arrangement here is a nitrogen in the center and some fluorines on the outside. You can think of it as like being four-sided. I happen to have put the fluorine there on the bottom. You could have put the fluorine up on top. It's all good. You could go top or bottom. It doesn't really matter with that kind of third fluorine. Now that I've done that, I'm going to now do the next step, which is just a good old-fashioned single bond from the center to everybody on the outside. So I'm going to draw me a line there, there, and there. Now, since each of these lines represents 2 electrons, I have now used 6 electrons up here in my picture. So if I subtract that off here from my total, I got about 20 electrons to go. Now, those 20 electrons are going to go on the outside first until everybody has 8 in dots, pairs of dots. So I'm going to go over here. So 2, 4, 6. That is now filled. It has 8 electrons. 8, 10, 12, that is now filled. It's got 8 electrons. And 14, 16, and 18, that is now filled. It's got 8 electrons. If I stop right at this point and count up all the lines and the dots, I have on my picture there about 24 electrons, if I am not mistaken, as I just put another 18 on there. Now I still have 2 electrons left. These then go to the center atom and also are put on as dots. Yeah. At this point, I have now used up all 26 of my electrons. The last thing I want to check is, does everybody have 8 electrons around it? So this fluorine on the right has 2, 4, 6, and 8 from the line. This fluorine on the bottom, 2, 4, 6, and 8 from the line. 2, 4, 6, and 8 from the line. Now when we look at the nitrogen, it has 2 from this line, 2 from this line, 2 from this line. That's 2, 4, 6, and 2 on the dots is 8. So everybody here has 8 valence electrons. They have all met what they want to do, which is what we talked about earlier. They have now all achieved noble gas configuration, in this case by sharing of electrons, and everybody's happy. That would be your correct Lewis structure without all the highlighting, but that would be what it would look like. Any questions on those steps? Those are the number of valence electrons from the group number. So if you look at the periodic table, nitrogen is group number 5. And fluorine is group number 7. And in this particular compound, there's 3 fluorines. So we have to multiply it by 3 for each of the fluorines that are present. Other questions? All right, why don't you try another one here, maybe? Let's try, why don't you do this one? Why don't you do, why don't you try a little carbonate, CO3 2 minus. So this entire thing has a -2 charge, 1 carbon, and 3 oxygens. Draw. Okay, let's take a look and see how we're doing on this one. Once again, we're going to take the same approach here. We know this is covalent bonding. Carbon is a nonmetal, oxygen is a nonmetal. So really we'll just get to sort of adding up our valence electrons. So once again, that's going to equal the group numbers. So carbon is group number 4 on the periodic table. So it's got basically 4 valence electrons. There are 3 oxygens, and each oxygen is group 6 on the periodic table. So that is going to give us our total for 6. Now in this case, this is an ion, and it has a -2 charge. And when somebody has a -2 charge or just a minus charge in general, it means that it has gained electrons. So it's important for your Lewis structure, you need to add those 2 electrons in. Otherwise, you're going to be a little short on your electron total here. So we got 18, 20, 24 valence electrons is our total number of valence electrons our picture should have. Now that we have that, we want to go with the least electronegative in the center. Once again, if you look at the periodic table, carbon and oxygen are in the same row on the periodic table. So as we were just talking about when we were looking at the electronegativity values, because of that, oxygen should be more electronegative than carbon because it's further to the right. And that means that carbon should be in the middle with oxygen around it. And again, you could put those 3 oxygens. You could go on top like I did there. You could put the other oxygen on the bottom. It don't really matter. We're going to follow our same steps, which is we're just going to do a single bond to each one. So we're going to go 1, 2, and 3. That again is using up 6 electrons, 2 for each line. That means we got something like less than 6 left, 18 electrons to go. That's going to go on the outside in pairs at this point. So we're going to go 2, 4, 6, and that is filled. 8, 10, 12, that is now filled. 14, 16, and 18, that is now filled as well. We have now put on our picture 24 electrons. Is everybody good at this point? Everybody is not good at this point, and it is the carbon here. If you count up the carbon, it's got 2, 4, and 6 electrons. It is short the 8 number. All the other oxygens have 2, 4, 6, and 8. So all those other oxygens are good. So in this particular case, our carbon is not good. It has not met the octet rule, which is basically the goal of what it wants to do. So we need to fix that. So can I fix it by just laying me up a couple dots there? Will that fix it? It will not fix it in the sense that obviously it fixed it, it gave it some more electrons, but now my picture no longer has 24. It's got 26, which is too many. So you cannot do that. So this is the part where we've done all single bonds. Now we're going to try to fix it by making a double bond. And in this particular case, you have 3 oxygens. Every one of those oxygens are identical to each other. So you literally could make the double bond at any oxygen you choose. Can I just make a double bond here by just putting a double bond there? I cannot do that for the same reason. I now have 26 electrons, and the oxygen up on top now has 2, 4, 6, 8, 10 electrons. That's too many, right? That's way more than 8. So what happens when we make a double bond? And honestly, when we make a triple bond as well, works the same way, is we actually need to take a pair of electrons and move them in to make that double bond. So I'm going to grab myself a pair of electrons up here on this oxygen, and I'm going to bring them in to make that double bond. And the result of that is I will now end up with a double bonded oxygen up on top. I will still have my single bonded oxygen on the right and my single bonded oxygen on the left. And since this is an ion, by the way, usually we put brackets around it, and we do put the charge on the outside to indicate that it is an ion in this particular case. What does that do? It now makes everybody good. If we take a look at our carbon, it's got 2, 4, 6, 8 electrons. If we look at the oxygen over here, 2, 4, 6, 8, 2, 4, 6, 8. We look at the double bonded oxygen, 2, 4, 6, and 8. Everybody has 8 electrons. If you count up all the electrons in this picture, it is still 24 electrons And that is also what we need in this particular case. So when you make a double bond or a triple bond, like I said before, it works the same way. You're just going to bring those electrons in to do so, to sort of fix it. First off, any questions on that there? Now, because you have the option in this particular case that all those oxygens are the same, you definitely could have made a double bond to the right instead and kept the top one single bonded, and you would end up with a double bond over here. Or you could have double bonded over to the left and kept everything else a single bond, and you would have ended up with a structure that looks like this. These structures are related to each other. Usually you'll see this little arrow heading in both directions. These are what are known as resonance structures. And resonance structures are structures where basically this happens. You have the option to make the double bond on the right or the left or the top. You have more than one spot where you can do that. The reason is because those electrons we brought in to make the double bond, they're what are sometimes referred to as being delocalized, which means they're not belonging to anybody in particular. So what's really happening when you look at something like this is those double bond electrons that we could use to make that double bond are actually moving around, and at certain times they may be over here, at other times they may be up there, they may be over there. Because they could be at any of those oxygens, we cannot draw a Lewis structure that's permanently like this is the only one that could happen. And the real structure is somewhere between all three of these. But any one of those structures that's on the bottom is a legitimate, valid Lewis structure for CO3 2 minus for carbonate. So if you're asked to draw the Lewis structure for carbonate, which in most cases is what you're going to be asked to do, you could lay up any one of those three and it would be perfectly correct. But there are multiple structures that can happen, and those are what are referred to as resonance structures when you basically have the ability to put that double bond in any of those locations. Any questions on that there? All right, so let's draw a few more here to make sure. Let's see. Actually, so let's see. Why don't you draw H2S? Why don't you draw CO2? Why don't you draw SO2? NH4 plus. Why don't you draw N2? And for the fun of it, why don't we do let's do nitric acid just for fun. By the way, nitric acid looks like this. Looks like an oxygen, a nitrogen, an oxygen and a hydrogen hooked together, and an oxygen. As you might not know how that's hooked together. All right, so take a few moments here for each of these. Draw a proper Lewis structure. See what you come up with. We'll start here with the top left. So H2S. So once again, the first thing I'm going to do is figure out valence electrons. So we have two hydrogens. Each one is one. We have a sulfur, which is group 6. So that is 8 valence electrons. In this case, we know for sure hydrogen should not be in the middle. So sulfur's got to be in the middle. We're just going to put hydrogen on either side. Once again, going to do our single bond to the center to the outside. That gives us now used up 4 electrons, 2 for each line. We have 4 electrons to go. Will I be putting dots on hydrogen? I will not. Hydrogen on both sides are filled at this point. Remember, they only need 2, which means as soon as they get that line, they are done. So same idea, since there's nothing to put on the outside, we still have 4 to go. We now go to the center, and once again, we're going to put those center ones on as dots or pairs of electrons, and we will end up with a picture that looks like this. Our sulfur in the middle has 8 electrons, 4 non-bonding electrons and dots, and 4 bonding electrons with the lines. And each of the hydrogen ones have 2 electrons through the bonding there with the sulfur. Any question on that one there? Yeah. Taking a look at the next one here. We'll go with CO2. Once again, going to count up our number of valence electrons. Carbon is 4, group number 4 in the periodic table. There's 2 oxygens. Each oxygen is group 6 on the periodic table. So that is 12 plus 4. 4 is 16 valence electrons. Again, looking at carbon and oxygen, they're in the same row on the periodic table. Oxygen is further to the right, which means it's more electronegative. That means the least electronegative carbon should be in the middle. And again, we're just going to kind of hook a oxygen on either side. We are then going to do our single bond from the center to the outside. That is 4 electrons. We now have 12 to go if we subtract that from 16. Those again are going to go on the outside of this pair. So 2, 4, 6, that is filled. 8, 10, and 12, that is filled. At this particular point, we have now applied all 16 electrons. Is everybody good here? Our carbon in the center is well short. It has only 2 and 4 electrons. All the oxygens are okay. So this is a situation, once again, that we're going to try to fix this by making a double bond. So to do so, we're going to grab either side, since they're both the same oxygen. We're going to grab a pair of electrons and bring them in to do the double bond. And that's going to give us now a double bonded oxygen on the right, a single bonded oxygen there on the left. And did we fix the problem at this point? We did not. It did get better. Our carbon now has 6, 2, 4, and 6 electrons, so it's getting close. So at this point, you do have an option. And again, as I mentioned before, you usually want to kind of run through all your options for double bonds before you move to a triple bond, because you may be saying, can I just triple bond it now? The answer is yes, but it will not give you the good structure that you should have for reasons we'll maybe talk a little bit about later on. But in this case, we do still have the option to double bond the other side. So before we move on to a triple bond, we want to kind of exhaust all of our double bond possibilities. So since we can do that, we're going to take a pair of electrons from the other side and bring them in. And now what we will end up with is a double bonded oxygen on both sides. And now we are in business. We have still 16 total electrons. Each of the oxygens get to 8 electrons by 2, 4, 6, and 8. And again, 2, 4, 6, and 8. And each of the oxygen, not really each, but the oxygen here able to get to 8 by 2, 4, 6, and 8. So everybody gets to 8 electrons. Once again, the other main important thing is we still only have 24 electrons, which is what we're looking for, until I obviously erased everything there with the eraser we did have before we did that. I'll just re-put it back here. I was almost getting it. We could pop that back together. And now I think we're back good. So now we are good to go in that case. Any questions on that one? I might even lost the line right there. All right. So taking a look at the next one here. That was H2S. There you go. All right. Wow, I feel like I lost a bunch of dots there on that. All right, put everything back together. All right, so next one is SO2. Actually, I'm going to do it on the next page just so it'll be easier maybe to see. A little higher. SO2 is the next one. And then we have NH4 plus, I think. All right, so looking at SO2 first. Once again, going to get our total number of valence electrons. We got 6 for the sulfur. There are 2 oxygens, also group 6, which is 12. And obviously that's for the oxygen there. That's 12, and 6 is 18 valence electrons. Once again, looking at sulfur and oxygen on the periodic table, they are in the same group, which means oxygen is further up, and it's going to be more electronegative. So once again here, the least electronegative in the center, which would be sulfur. Going to do our single bond, 1 and 2. That is 4 electrons. leaving us 14 more to go. So 2, 4, 6, 8, 10, and 12. At this particular point, I have put 16 electrons on my picture. I still have 2 more to go. So those 2 actually end up right there on the sulfur as dots. That is how those dots get there. This is not a double bonded on both sides situation, yes? So there needs to have those dots there. At this point, we now have 18 electrons, and hopefully you can recognize that perhaps here our sulfur is not so good. It has only 6 electrons. So here we're in our double bond situation. It absolutely does not matter in this case which oxygen you choose, as they're both the same. We're going to take a pair of electrons from an oxygen and bring it in. And in so doing so, we will create a structure to look something like this. Double bonded on the right there and single bonded on the left. This is also another one that you could have done a resin structure. So instead of double bonding on the right, you could have double bonded on the left. And if you did that, you would end up with a equivalent picture where the double bond's on the other side. Still the 2 electrons on the center sulfur, and we would end up something like this. Any question on that? So you definitely want to make sure you follow the order that we talked about. I again cannot tell you how many people will draw this one with 2 double bonds on both sides, no dots on the center. So again, you got to kind of follow that to place all the electrons first before you double bond or triple bond. Any questions on that one there? Here we have NH4 plus next. And again, doing electrons here. Nitrogen is group 5, which gives us 5 electrons. There are 4 hydrogens, each are 1. Now, this has a plus charge on it, and a plus charge means that we have lost electrons. Plus 1 means we lost 1 electron. So we actually need to subtract 1 electron in this case because of the charge. And that's going to give us 9 minus 1, which is 8 valence electrons in this case. Nitrogen should go in the middle because hydrogen cannot. And we're going to put hydrogen on each side. Going to do a single bond to each. That, if I am not mistaken, is 2, 4, 6, 8. That is it. Everybody's good. And we will now have our structure there. Again, put little brackets around it and the positive charge. Any questions on that one there? And I think the very last one, we have an N2. Yep, N2. Let's take a look at that one. So we have N2 and HNO3, which is nitric acid. We'll start with N2. All right, so starting with N2, obviously that is 2 times 5 for the nitrogen. That is 10 valence electrons. In this particular case, there is no central atom because there's only 2 atoms involved. So you just go side by side and follow the same sort of process. So here I'm just going to put the 2 nitrogens side by side since there's nobody in the center. Going to do a single bond. That's going to leave me 8 electrons left. That's going to go 2, 4, 6, and 8. At this point, that is all 10 electrons on my picture. The nitrogen over here is very short. It has only 4 electrons at this point. The one on the right's actually good. It's got 8. So we're going to try to fix it by a double bond. We're going to take some electrons from the guy on the right and bring it in to make a double bond. That will then give me a double bonded nitrogen. That looks something like this. That got me close. It did not fix the problem as this nitrogen here still only has 6 electrons. There is no other place for me to make another double bond at this point. So now I am ready to make a triple bond. Works the same way. I'm going to take a pair of electrons from this guy and bring them in to make my triple bond. And when I do so, I will end up now with a triple bond in the middle. And now each nitrogen has 8 electrons for a grand total still of 10 electrons total in that picture, and everybody is happy. Any questions on that there? All right, last one here, nitric acid, which is a little different. And the reason I'm showing you this one is just to illustrate that you can have more than one central atom. So not everything will have one. Most of the things you draw will have one central atom, but things can have multiples. As I mentioned before, the arrangement of this guy does look something like this. And if it happens to be something that you might not know the arrangement, I would tell you, obviously, like I did here, how things are hooked together. So we're still going to count up our total number of valence electrons here. So hydrogen has one, nitrogen has five, and there's three oxygens, each has 16. That's 18, 19, 24 valence electrons when you add that together. Even though there's multiple central atoms, there's the nitrogen in the middle and the oxygen to the right there, we're still just going to do our same process, a single bond to everybody. In this particular case, now I've used 8 electrons, 2 for each of them. That leaves me now 16 electrons to go. I am still going to work on the outside and work my way in. I am definitely not, because we're professionals here, put any dots on the hydrogen, right? So it's good. So we're going to go then 2, 4, and 6, 8, 10, and 12. At this point, I have now used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, if I am not mistaken. Again, I'm going to just count that real quick one more time. 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20 electrons. I still have 4 more electrons to go. The next outside atom is actually the oxygen on the right there. So we're going to go 2 and 4. And now I have put on there 24 electrons. Is every element in this one good? It is not. The nitrogen is short in terms of electrons. It only has 6. Once again, we're going to fix this by making a double bond. You actually can make the double bond at any place, but we are going to make it here and bring it in. And that will get us something that looks like this. You could also do a resonance structure where you double bonded to the left instead, and you would look something like this, where that is single bonded. In most cases, you probably wouldn't mess with this part, because that's actually what makes it an acid. That hydrogen that comes off there is actually what makes it an acid, and that's a polar bond between the oxygen and the hydrogen, so you probably wouldn't play too much with that. Any questions on drawing Lewis structures?